In today's video, we'll learn about the ideal gas law. Before we learn about the ideal gas law, we'll have to understand what an ideal gas is. An ideal gas is a collection of atoms or molecules that move randomly and exert no long-range forces on each other. Each particle of the ideal gas is individually point-like and occupies an unmeasurable amount of volume, and that most gases at room temperature and pressure behave approximately as an ideal gas. We see that the equation we get from the ideal gas law is PV is equal to nRT, where P is our pressure, V is our volume, N is our number of moles, R is our universal gas constant, which has a constant value of 8.31 joules per moles Kelvin, multiplied by our temperature, which is measured in the Kelvin scale. So if we look at our figure to the right, we see we have the ideal gas law summarized with the definition of each variable. And at the bottom we see that we can manipulate the ideal gas law to solve for any of our 5 variables. In the ideal gas law, we use moles as one of the variables. And moles is an expression of the amount of gas in a given volume. And we see if we're given the mass, and we know its molar mass, we can take the mass divided by its molar mass to calculate the number of moles. If we want to know how many particles are in a mole, we can use Avogadro's number, which is a constant which is equal to 6.02 times 10 to the 23rd particles per mole. And by using Avogadro's number, the mass of an individual atom can be calculated by taking the molar mass divided by Avogadro's number will give us the mass of our atom. If we look at our figure to the right, we see we have a triangle that has a mass, moles, and the formula or the molar mass. If we know 2 out of the 3, we can convert between either of the 3. So if we have mass divided by moles, it'll give us the molar mass. If we take moles multiplied by our molar mass, we would get the mass. Or if we took mass divided by the molar mass, we would get the number of moles. So we see that this triangle is just a helpful way for us to keep track of our conversions between the 3. We also see that there are alternative versions of the ideal gas law, one being PV is equal to NKBT, where Kb is Boltzmann's constant, which has a value of 1.38 times 10 to the negative 23rd joules per Kelvin, and our capital N is the total number of molecules, which is different than our lowercase n, which was the number of moles. In our first example, it states an ideal gas occupies a volume of 1 centimeter cubed at a temperature of 20 degrees Celsius at atmospheric pressure. And we're asked to determine the number of molecules of gas in the container. So what we're asked to solve for is capital N, our number of molecules in the container. We're given the volume of the container, which is 1.0 centimeters cubed, or if we convert it into meters cubed, we would get a value that is equal to 1.0 times 10 to the negative 6 meters cubed. And given that the temperature is 20 degrees Celsius, which we can convert into the Kelvin scale by adding 273, which will give us a temperature of 293 degrees Kelvin. And it states that the pressure is at atmospheric pressure. So at atmospheric pressure, 1 atm times 1.013 times 10 to the 5th will give us our pressure in pascals. So if we use the equation of PV equals nRT, we can rearrange this equation to solve for our moles. And then once we have our moles, figure out our number of molecules. So when we rearrange our equation, we see our equation will be PV divided by RT. If we plug in the values we're given, our pressure is equal to 1.013 times 10 to the 5th pascals multiplied by our volume of 1.0 times 10 to the negative 6 meters cubed divided by R, which is a constant of 8.31, times our temperature in Kelvin of 293 degrees Kelvin. When we calculate this out, we see that the number of moles we're left with is equal to 4.2 times 10 to the negative 5th moles. Now that we know our moles, we can take our number of moles multiplied by Avogadro's number will give us the number of molecules of our gas in the container. So if we plug in our values, we see that we have 4.2 times 10 to the negative 5th moles multiplied by Avogadro's number, which is 6.02 times 10 to the 23rd. And we calculate this, we see that the amount of molecules of gas in the container is approximately equal to 2.5 times 10 to the 19th power of molecules. And part B, whereas if the pressure of the 1 centimeter cubed volume is reduced to 1 times 10 to the negative 11th Pascal, while the temperature remains constant, how many moles of gas remain in the container? So if we look at part B, and we take our pressure times our volume is equal to nRT for our first case, and we compare it to our pressure, our volume equal to nRT for our second pressure and our first pressure, we're given that our temperature remains the same, so we can cross out our temperature. R is a constant, so we can cross out R, and it states that there's no change in volume. So we're left with an equation where P1 over P2 is equal to our number of moles of 1 divided by our number of moles of 2. And we're asked to find how many moles of gas remain in the container. So if we rearrange this equation to solve for N2, we would get an equation that states N2 is equal to N1 multiplied by our second pressure divided by our initial pressure. With our pressures given and the number of moles we calculated in part A, we can solve for the final number of moles there will be. So we see that N2 is equal to the number of moles in the container for our first scenario, which was 4.2 times 10 to the negative 5th, multiplied by our second pressure, which is stated to be changed to 1.0 times 10 to the negative 11th pascals, divided by our pressure at standard atmospheric pressure, which is equal to 1.013 times 10 to the 5th pascals. So if we divide our pressures and multiply by our initial number of moles, see that the final amount of moles left in the container will be equal to 4.146 times 10 to the negative 21st moles. In our second example, it states that a popular brand of cola contains 6.5 grams of carbon dioxide dissolved in 1 liter of a soft drink. If the evaporating carbon dioxide is trapped in a cylinder at 1 atm and at a temperature of 20 degrees Celsius, what volume does the gas occupy? So we're asked to solve for our volume. We're given that the mass of the carbon dioxide is 6.5 grams, and our pressure is at 1 atm, which is equivalent to 1.013 times 10 to the 5th pascals, at a temperature of 20 degrees Celsius, or if we convert that to Kelvin by adding 273, we see our temperature would be 293 degrees Kelvin. By looking at the ideal gas law, where PV equals nRT, we see that we're given our temperature, R is a constant, pressure is given to us, and we can solve our moles since we're given the mass of carbon dioxide, and we can calculate the molar mass of carbon dioxide. We can solve for our moles, so we can rearrange the equation to solve for our volume, which will give us our number of moles times R multiplied by our temperature divided by our pressure. And we know to calculate moles, we can take the mass of our carbon dioxide, divide by its molar mass, and since carbon dioxide is CO2, you know that one carbon is approximately 12 plus one oxygen has a mass of 16. Since there's 2, we times that by 2. So we see that the molar mass for carbon dioxide is equal to 44 grams per mole. So if we divide our mass by our molar mass, see that our moles will be equal to 0.1477. So now that we know all our variables, we can solve for our volume. So our amount of moles is equal to 0.1477 multiplied by 8.31 times our temperature in Kelvin of 293 degrees Kelvin, divided by our pressure at standard atmospheric pressure, which is equal to 1.013 times 10 to the 5th pascals. We see that our final volume will be equal to 3.55 times 10 to the negative 3rd meters cubed. However, since we're given it in liters, we know that for 1 meter cubed, there are 1,000 liters. So our volume, after it's converted into liters, will be equivalent to 3.55 liters.